Listen up. We're going to talk about noise today. And when I say listen up, I mean LISN, Line Impedance Stabilization Network. If you're interested in noise, as every single SWL, ham radio operator, NDB hunter should be, stick around because we're going to do some testing. W1VLF. Hey everybody, my name is Paul, W1VLF, and welcome back to the lab. Today what we're going to talk about, and going to try and do a series on this, is this box. We'll go inside of it in a little while. LISN, and everybody's favorite noisemaker. This is one of the really inexpensive battery chargers. But before I get into that, I want to get a little housekeeping out of the way. The LIL, the low impedance antenna, is not dead by any means. I just wanted to pull away from that for a little while and do this video on noise. And so that's coming back. In fact, well, in the meantime, I had made a few different improvements to it, keeping the 4 foot, the 2 foot by 2 foot size, and approximately 6 dB, maybe a little more, down at 24 kilohertz, and made a number of improvements on that. And the second thing I want to say is, what do you think of this? My daughter-in-law Nicole and her son and my son Steve made these shirts up for me. Dad, you can't go on there like that. You got to have your call sign on there. So I said, all right, you're right. So they made these really cool shirts for me. So I got one in yellow. Oh, they also made this really neat sticker for my coffee cup. So that's great. So I want to give them a shout out and thank them for taking the time to do this for me. In fact, one other quickie here is Steve has been working on, my son Steve's been working on a CNC machine, and he's made some of these hoops for me, and I'm forming them into a loop. So later on down the road there'll be some more loop videos coming up. But anyway, right now we want to talk about the LISN. And the LISN, it sounds just like what you would use it for. Listen, LISN, L-I-S-N. It means a Line Impedance Stabilization Network. And so what is that thing? What is it? Okay, well, your device under test. Let me bring the camera down a little bit first. Okay, so a close-up of the LISN itself. What is this? What is this thing? What it allows you to do is to add a source of power in the back, the AC input here, and plug some device into it. All right, and the some device in this case is going to be a battery charger. This is a run-of-the-mill battery charger, battery tender sort of thing that you can get anywhere, and who has not had noise problems from these guys? And we're going to take a look at that on the spectrum analyzer over there. Now, a couple of things I'd like to say about this is you have two outputs here. One shows the noise on the, which is at the line side, and the other one shows the noise. This is backwards in the screen. Anyway, it shows the noise on the neutral line. But basically what it does is it allows the 60 hertz in and to power your device, but does not allow it to come out these two ports of the spectrum that your spectrum analyzer connects to. And when you connect your analyzer to it, you're able to see from 150 kilohertz up to 30 megahertz with this particular LISN and this particular design on either the AC line, the hot side, or the neutral side. It also disallows garbage from coming up the AC line into the LISN and coming out this port and allowing it to get to your spectrum analyzer. So truly what you're testing is this guy right here. Now, when we talk about noise, and we're only talking about man-made noise here, there's two things that we need to consider. One of them is conducted noise, and the other is radiated noise. And what does that mean? Well, conducted means, here's the little box, okay? And if you think, let's just talk about, look at this for a second. This looks like a dipole with a transmitter in the middle, right? Kind of a crummy dipole. Let's say, how well do you think this little box with these tiny little wires radiate at 75 meters? Pretty horrible, actually, right? Because it's only a foot long on either side. So, yeah, I'm running a 2-foot dipole at 6 inches off the ground, and how are you copying me? The problem is that if you don't stem off the RFI that's generated internally in here, guess where it goes? It comes out this port, the power line port, and now as soon as you connect this to the AC line, you have an infinite antenna. Who knows what you have out there? You have long wires, you have loops internal to your house that change when you turn a light switch on, it completes a loop. There's so many different things that you don't know about. So the FCC says you can build whatever you want in this box, but don't let it come out this side. Unfortunately, this particular box, and many of them like this, it comes out this side and this side. And the other, so that's conducted. It's conducted onto these wires, right? But when you conduct something onto a wire, like your feed line or the center of your feed line, eventually it gets radiated. So keep garbage off of the AC line and keep garbage off of this. Now we're going to look at this battery charger, and I want to say hi to Bob up there in New Hampshire who corrected me. It's a battery charger. But I'm also going to be testing a power supply. And so what this box here does, the LISN, allows you to see, well, what's coming off of this? You know, what kind of emissions are conducted onto the AC line? So it strips it off and you check either one of these ports. So that's why that kind of thing is really important. A couple other things. If you were to do this and use this as calibrated information, first of all, you'd need to have not a homemade LISN, but a real honest-to-God LISN, $5,000 or $10,000 box like a Roden Schwartz or someone else like that. It would also have to be on a specific ground plane of 4 feet of metal floor, metal backing. So what we're going to do here is we're not going to say this thing passes, well it doesn't, passes or doesn't pass FCC regulations. What we're going to say is, let's see how bad this is and compare it to other things. So everybody's had this problem with a battery charger running. Especially now, right? Especially in the wintertime when you think about, well, I just want to slap this on my car that I only drive in the summer because I don't want the battery to go dead. So these things, and this is a relatively small supply. This is capable of 1.5 amps of current. So we'll run this battery charger on a power resistor, and we'll turn it on. We'll test it with it just plugged in. We'll test it with wires connected to a resistor. We'll also test it in something that's a lot more like its real-world environment. These wires can radiate if there's noise on them, but they're kind of short. But think about what happens. The plus goes to the battery on your car. That means all the internal wiring is connected back to this thing. And the minus goes to this huge monster body of the car. So you got some pretty good radiators. So this test won't be valid for an in-service and the way it's actually mounted and used in service. So what I'll do is after we do some tests, I'll actually connect a piece of wire to each one of these. And we'll see what happens to the amount of noise that's pushed back into the power line. Okay? And then what we're going to do is this. Let me just grab this piece over here. I have the W1 VLF mystery box. Well, there's no mystery. I made it, so I know what's in there, but we'll talk about this later on. So today I want to cover a few things. The LISN a little bit, and I'm going to do that right now, kind of do it over on the other computer so we can see what the schematic of this looks like, and why we use it. And then maybe what's inside this box a little bit later. We'll go over to the analyzer and we'll grab a couple of screen captures of this device just plugged in, this device actually making power, and also this device with real-world couple of wires connected to it. And let's see what happens. So anyway, I'm going to run over to the desktop computer there, fire up the microphone. We'll just take a look at the LISN and talk about it really, you know, in basic terms. Again, none of these things are you know, up to FCC spec or would pass muster. This is not the right environment. I don't have the right detectors in my spectrum analyzer. But for comparative reasons, I think you're going to find, hang on, let me grab one more thing here. Here's a little switching power supply. What's this? Jet stream, right? We're going to take a look at this jet stream making, well, I don't know, 10 amps or so. And we're going to look at this thing making 1.5 amps, and we're going to see just how much garbage is put onto the power line. So let me run over to the other computer and grab the schematic of the LISN. We'll talk about that real quick, and then we'll be back in here and set up for some more stuff. Okay? All right. Be right back. Okay, here we are with our schematic diagram of the LISN. LISN, Line Impedance Stabilization Network. So we'll go through this real quick. This is in the LISN you saw on the desktop. There are two sections, so this is really just one section, one for line and one for neutral. So what do you have here? Well, here between E and L or E and N, depending on if you have two or one of these, that's where your AC comes in. The mains come in here. Okay. And so the first thing that the mains see is a 1 microfarad capacitor, which looks like, let's see if I have my numbers right here. At 60 hertz, it looks like 2,600 ohms. Okay. And at 60 hertz, you have 50 microhenries. Am I getting this right? Yeah. At 50 microhenries, the 60 hertz passes right through there. It looks like less than a tenth of an ohm, 20 milliohms. So basically, this straight line, this is where your device connects over here, between here and here. So coming in at 60 hertz, this looks like a 2K resistor. So it does absolutely nothing. The reactance of this component is 0.019 ohms. So it does absolutely nothing, right? So now you have AC power coming to your device, which is out here from this point to this point. Now this is a 150 kilohertz LISN to 30 megahertz. We're not going to use it all the way up there. We'll look at it real quick, but then I'm going to limit our scans down to something that's, you know, we're more interested in, and typically these noise-making devices affect us on the lower bands. So let's take a look at 150 kilohertz. Okay, so any noise coming this way, right, at 150 kilohertz, this capacitor, C1 here, looks like 1 ohm. So it's going to short that out, and it's not going to go in this direction. The 50 microhenry LISN, and these are standard values, by the way. There are a number of different standards, but in this case, these are standard values for this type of LISN. And so we'll just go through here. So at 150 kilohertz, you have essentially 1 ohm to ground here across these two, and then in series with this leg, you have 500 ohms. Okay, so not much noise in the bands that we're interested in from 150 to 350 are going to get through. Okay, because if they did, they would go down through this capacitor and out. So essentially, there's no noise here. That there may be a little bit, but for what we're looking at, we're going to see some pretty dramatic changes. So now you've powered up your device out here, and the device is coupling energy, conducting energy, if you will, onto the power line. So what happens? Well, from here, this is the reference ground, or the reference neutral side of the analyzer, because your spectrum analyzer or test receiver is going to go here. So let's see, 60 hertz. How well does 60 hertz that's making it to this device go down through this 0.01? And that 0.01 looks a lot like a 26,000 ohm resistor. So there's not much getting through there. And at 26,000 ohms in series with this, it means it's essentially at 60 hertz, pulled right to ground. So you don't have to worry about 60 hertz, 120 volts coming out, going to your spectrum analyzer. But at 150 kilohertz, this capacitor looks like a tenth of an ohm. So whatever's on these two, whatever's on this line, whatever's conducted on this line gets ported out that way. And again, going backward, trying to get backwards through here, it's 500 ohms. And then trying to get back towards the line, it's 1 ohm on this resistor. So this is a diplex filter, essentially. 60 hertz passes through unscathed, starting at 150 kilohertz. The only path out of it is out the test port here, and this is where we're going to take a look at our at all the different energies that we're gonna look at. I'm going to run over after, well, not after, but right now I'm going to run over and we'll pop the LISN apart so you can just get a quick look inside, and we'll poke around a bit, and then we'll start some of our testing. So stand by for that. Okay, so this is the LISN right here. We're going to pop the cover off it. There's only really 2 screws. I think if I was to build it, this is a homemade unit, and if I was to build it, probably would build it in a very well shielded box, so that my local 610, which like you know is out that window, would be able to not sneak in here, and it does a little bit. So simple cover comes off. Let me grab the camera, go handheld, and we'll poke around inside this. Let me set the bail down so that. Wow. All right, let's turn it this way. How's that? Let me grab the camera. Okay, so what you're seeing here is the 150 microhenry, or excuse me, the 50 microhenry inductors. Now you have to remember that we're going to be actually drawing current through this device, through this LISN. So the inductors can't be small, number, 30 wound inductors that will burn up when we try to draw a couple of amps through here. So here's one side. This is the neutral side. This is, yes. This is the line side, the neutral side. And coming in off the power, you have capacitors to ground to short out any garbage that's coming in from the line, and also provide reference to ground for anything that might make it back through these 50 microhenries. And then there's, of course, some 0.1s over here. And that 0.1 is in series to ground with a 1K. And that goes to the test port, the output port. So not a whole hell of a lot to it. In the real world, these would be damped with resistors across each one. But for our purposes, for the home lab like this is a really great box. Again, we don't have the actual environment to test on an FCC basis, or even what's called pre-compliance. We don't have the calibrated LISN, and we don't have the right detectors in the spectrum analyzer that we're going to use. But we have enough to approximate, and we can see what different power supplies, what different battery chargers look like. So I'm going to, let's see, what am I going to do now? I think what I'm going to do is put this back up on the camera, put the lid on, and ooh, there's the W1 VLF mystery box. And oh, here's my the battery charger in question. And I got a couple of battery chargers. This is a switcher, and I think over in the box I have a couple that are not switchers. But we're going to compare a few of them, and then we'll go through some tests. So let me put this baby back up on the tripod and get set up for this test. Okay, we're back. All right, so we have the LISN in position right here. First thing we're going to test is this switching power supply. All switching power supplies are no good, right? Not necessarily. And if you look up here at the spectrum analyzer, we're going to connect the spectrum analyzer to the LISN. And I'm going to use a method called peak hold, or maximum hold. So we're on, number 1 is the black trace. And so we'll go to max hold. And it's just showing basically the noise floor of the instrument, the LISN. Nothing else is connected. By the way, I have a 10 dB pad in here, which does not make any significant difference when we're testing the noise floor of the instrument. But just remember, everything that you see is going to be 10 dB lower than it is in real life. And I want a 10 dB pad in there in case something goes haywire and my analyzer doesn't get blown up. So we will stop trace number 1 from capturing. So we're just going to hold it there. Let's move to trace number 2. Trace number 2 is blue. And what we're going to do now is hook up. We'll connect the jet stream to a 2 ohm resistor. So 2 ohms at 13 volts is, well, let me turn this around, is roughly 6 or 7 amps, right? I don't know exactly what this is going to be running at, but let's slap this on. Actually, no. Let's use number 2. We'll turn on the power supply. It's not plugged in. Let's plug the power supply in first into the device under test, commonly referred to as the DUT or the EUT, electronics or device under test. So when we fire it up now, and before I do that, I'm going to put up the second clear and right. I'm going to put up the second clear and right, number 2, hide, update. Okay, so we have to update it and unhide it. So there's basically our noise floor again. So I'm going to turn this on and let's see what happens. Let's see all the noise that comes out of this. Okay, I just turned it on. It's up at 12.5 or 13 volts, something like that. And let's go to another peak hold. I'm using peak hold just so that we can have some cleaner traces to look at. So let's go back into here and go to our max hold. Okay. And I don't know, it looks pretty damn much the same. There's a little bit, if you look in here, there's a few places where there's a little bit of noise. So let's stop that one from updating and let's turn on number 3, which is going to be the green, and we'll just we won't hide that. And we're going to go to clear and right. Okay, so now we're actually going to load this power supply. So a lot of noise isn't generated until you make the power supply do some real work. So we're going to put this on here, and here, and whoop, wrong end, here and here, and now we have about 7 amps. So we're going to do a peak hold on this now. Or max hold. So it's not a hell of a lot of difference there. That power supply is pretty quiet. I'm going to turn the voltage up. That's as high as it goes. But there is a little bit of noise here. Let me stop this from updating, and we'll peel away the 2 3 is max hold. That's loaded. The green is with loaded. We're going to hide that. The blue is with no loading on it, so that's number 2. We'll hide that. And then here's the black, which is the baseline of the instrument. So let's go back to number 3, which is the loaded instrument, and we're going to unhide that. You could see, right, turning it on and off. Yeah, there's a little bit of noise there. Considering this is the baseline of the instrument, this is really nothing to write home about or nothing to worry about. So I would say this thing is pretty clean. Now remember where this is, right? Minus 90 is this baseline. I'm not going to change that baseline because that's just this instrument over here. And then what I'm going to do is I'm going to switch out to the other battery charger, and we're just going to plug it in. We're not even to pull any current from it. So again, just for review, this is the Jetstream pulling 7 amps. I saved these. So that is the baseline of the instrument. Number 2 is it just idling. Okay, so there's a little bit of noise. And then, number 3 is, I'll unhide that, is pulling 7 or 8 amps. So it would probably be slightly worse than this, but this is not bad. So let me clear those number 2 and whoops, what happened? Traces. Let's clear number 2. We'll go clear and write, and then number 3 we'll go clear and write. All right, and they're not updating right now. So let's disconnect this, which I shut it off. And that resistor is very hot. Okay? And we're going to switch out resistors. Whoops. Here's the other resistor. This is 10 ohms. So it's about 1.5 amps, which is what the rated power supply, battery charger is here. So without doing a damn thing, not even turning this on, I'm just going to plug it in, and we'll fire up number 2. Let's go to number 2, which is the blue trace, clear and write, and we're going to update it. And of course, there all you're seeing is the noise floor right now. So let's plug this baby in. Let's take this out of here. We'll unplug this. I hope this is coming out okay. And we're not even going to load this. In fact, if you look at this really right here, there's dead charge and power. All we're going to do is power it up. It will not even be charging. So if you just left this plugged in somewhere, this is what would happen. Okay, so here goes. Okay. So now let's go to let's do a max hold here and see where that shows up. So it's a little bit difficult because we're looking at 30 megahertz. So I'll tell you what, most people don't have problems above, let's say, 40 meters. So we'll go and we'll make this span, instead of 150 kilohertz to 30 megahertz. Let's take a quick pause here. I'll unplug this, and we'll do the same test over again. We'll set our stop frequency up to I don't know what, 5 megahertz. So then we'll be able to see a lot of the individual carriers. So let's go back to clear and right there. And number 1 is going to be our baseline. So let's turn it on, update it, and we'll do max hold. Okay. We'll turn 2 off for a second. Oops. Turn it off. Okay. So there we are, right? That's 80, that's 100, minus 90. So we'll stop updating that, but we'll leave it on. All right, so let's go and turn on clear and write. let's see, an update. So if I did the same thing, max hold over here, we would see the same noise as we did before because I haven't plugged anything in yet. So let me go and clear this off. Clear and write. Now we'll plug in the battery charger right here. No load on it. In fact, it's not even turned on yet. It's just sitting around idling. Okay, so now we can see. Oh, I forgot. Sorry about that. You got to go back to 1, and you got to go clear and write. Clear and write. And number 1 will max hold. And then I have to stop number 1 from updating. It didn't. Okay, that's enough. Take the update off. Now we'll go to number 2. Okay, here we go. We're going to plug it in. Okay, so now look at all these peaks from 90 to, what's that? 10, 20, 30, 40. But let's so we're on an even playing field here. Let's do a max hold and see where these all end up. And the reason why, excuse me, the reason why I'm doing this at 2 megahertz or 5 megahertz, so you can see how much power is coming out of this thing. I don't know if you can see that. It's not even charging yet. Not even charging a battery yet. So let's not update that one anymore. We'll stop. And let's turn on number 3. Turn that on. Okay, there's our noise level that's coming out of this device. Now what I'm going to do is I'm going to hook it up to the battery. Now this battery, excuse me, this resistor here, this resistor is set up so that it's going to draw 1.5 amps. I've got it so that it's going to draw the rated load. Now in order to make it come on, because it's not a battery, this little device here, see the charging light is not on? We'll have to pop it really quickly with 12 volts. And you watch that green when I do that. Okay, so the green just, now the thing is on and it's actually doing some charging. And let's go in, do a max hold on that. Okay, so now we don't just have little spikes anymore. We have just about a right across the line noise level that is, oh, I don't know, let's see, 10, 20, 30, 40 dB above the ambient noise of the machine. Okay, so we're going to do, now this is of course with these 2 little wires, and these 2 wires go into a battery. The battery has some physical size, but the reality is the battery's in the car. This is designed to be a tender where you leave it on all winter long, right? So this is not really fair, just taking this, you know, it's not representing the body of the car. Well, all the wiring in the car would be connected to, oops, all the wiring in the car would be connected to the positive side, and the ground, the whole body of the car would be connected to the negative side. So let's connect a couple of wires to this that will represent that. I'm going to turn off number 2 because we don't. Let's hide that one. And what we have is the battery charger running that resistor at its rated value. And what I'm going to do now is turn on number 4, which is red. Turn it on, clear and write. Whoop, update it. Okay, so what we're updating is we're seeing the noise coming out of it. So here, let me connect up my pseudo. Oops, hope that didn't shut it off. This is what it might look like in the real world connected to a car. Okay, so I'm going to just put a clip lead on there, and a clip lead here, and we'll hook it up to a piece of wire on the ceiling. This wire is only 5 feet long, And I'm going to do the same thing on the other side. Connect the clip lead. Because you know we always use clip leads here. Alright, now we'll do a peak hold and see what that looks like. Or max hold. They call it max hold. Okay, well, it's higher in a lot of places, but not as much higher as I thought it was going to be. Let me put my hand on it here and see if it makes any difference. But look at the baseline to the top of the noise. 10, 20, 30, 40, 50. 50 dB above whatever level was coming out of that jet stream. Let's take a quick look over at the 75 meter receiver SDR in the other room. All that crap. I may make this into an insert. I have it running. Okay, so S9 plus 14, something like that. Now if I pull off those clip leads, you'll see that that drops down somewhat. In fact, we'll make a quick run over there and we'll yank those clip leads off. Our pseudo car, not pseudo, but okay. So you can see that it dropped off significantly. So let's do another test. We're going to insert a filter into the AC line and see how much noise we can eliminate by using the proper EMC filter. Put you back on the tripod over here. I guess you can still see what's going on. And what we'll do now is we'll take the mystery filter here. Well, let's clear some of the stuff up on the screen here. Let's get rid of number 3. We'll turn that off. And actually, number 3, clear and right, will become the filtered output of the battery charger. So let's plug in the mystery box. Set that right there. And it's on, but it's not making power. Hold on. These things have a relay in them so that they will not try to charge no load, and if you short them, they won't try to charge a short either. So let's turn it back on. It's on now. And let's do a peak hold with the filter inside. Where is it? Clear and right, and a max hold. So let's hook our car body back on. And let's hook our, where'd the rest of our car body? Oh. This is a car body over here. And so look at the difference here. With that EMI filter in place, we have only about 10 or 12 dB above the noise floor of the passive device, right? This is a passive device. It doesn't make that much noise. But look at this. Without that, we have, let's say 5 let's say 5 more there. So 5 and 5 from the bottom is 10 and 20 and 30. Wait a minute. There's 5, 10 is 15, 25, 35, about 40 dB of difference, roughly. So let's just make one small change here. We're going to go back to clear and right on the green, and we're going to pull out the filter and we're going to pull that filter out, and we're going to plug the battery charger back in again, which means I have to start it with a 12-volt zap here. Okay, now it's on. And we still have our car body and our electrical wiring inside there. And we're going to do a max hold. And it's right back up where it was. So, some interesting stuff going on here. I could tell you that when you take this apart, you are not going to find EMC filtering on this side, the DC side, or the AC side. So let's try a quick test here. Let's try a quick test. I'm going to grab a 0.1 microfarad capacitor. So whatever I got on the shelf here. This is a 0.1. This is a 0.1. Okay. So what I'm going to do is, as you can see, the peak up here is pretty noisy. So let's shut number 4 off, or we'll send 4 back to clear and right. Okay. And now what I'm going to do is I'm going to grab a hold of a 0.1 on the positive side, and then I'll connect it up to the ground, and then I'll connect the 0.1 up to the negative side, the car body side, and we'll connect that up to the ground wire. Let's just see if that makes any difference. That's nice, huh? Nope. Shorted it out, so I got to start it up again. Okay. Okay, so now we're going to do a peak hold here. Not too much difference. Okay, but let's put that in. It's a little bit of difference. It's about a 5 dB difference. Let's put the line filter in. So we're attacking this from both directions, as we should have been if we manufactured our power supply, our battery charger correctly. So let's go to clear and write that one, and let's go to max hold now. Okay. So we're about 10 dB above the noise floor instead of 50 or 60 dB above the noise floor. So, tell you what I'm going to do. I'm going to pop this box open here. Whoops! I don't even know if you're looking. Oh yeah, I guess you're still on target. I'm going to pop this box open, show you what's inside. It's nothing special. It's just a line filter, a right off the shelf line filter. Okay, so let's take a look at these battery charger, the power supply, and the EMC filter. First thing we're going to do is we're going to pop this open. Let me zoom in and we'll see what's inside here. I'm not going to open this up because this is already pretty well filtered. We could see that there was no conducted emissions or very, very little conducted emissions coming out of this. Not the same for this guy. And let's zoom in and take a look at what's inside here. All right, let's see what we got inside this box here. Just unscrew it. This is a Carlin box, model number 34481-06681. Actually, that's some number. That might be the Home Depot's number, but this it may be an E989NNJ. In fact, that's what it is. E989NNJ. Available for like $4 at Home Depot. Watertight. Great for building all sorts of stuff. I think the guy at Ballon Designs uses these for his outdoor Ballons. Because the Ballon on the antenna I have is exactly the same as this. Okay. So, there it is. Going to zoom in on that now. Okay, looks like you could probably see it okay. So it's a Corcom filter. This is not anything special. This is something I had on the back shelf. But basically, the power cord comes in. All three lines come in. You know, all three. The white, the neutral, the hot, and the ground, and they all go into the filter, and they all come back out of the filter. And if you look in there real close, without whacking the, see if I can get that a little bit better. I'm doing this upside down. Okay. You have line on one side and load on the other side, and there are capacitors across the line for differential mode canceling, and then there is a let's see, it's hard to see it, but there's also a common mode choke in there, another differential mode capacitor, and also a couple more common mode to ground capacitors. But these things are available anywhere. Surplus, cheap. This one is good for 3 amps. It's small. I don't use it for anything big, but that's what's inside this box. And I also use these things called Wagos. Look these up sometime if you get a chance. These are called Wago wire connectors. Let's see if I can get one of them in the picture here. Really nice. These are good for 20 amps a piece. Your wires go in and they just snap shut. No more twisting your wire nuts or anything like that. All right, so let me zoom back out a little bit, and then we're going to take apart the battery charger, and let's just see what the hell is in there. Oh, again, this guy should be built into this guy, but don't believe it, because if you want to make this cheap enough, this battery charger cheap, you have to take something out. So let me zoom, let me set the camera up a little bit better, and then we'll take this apart. Alright, let's pop this baby apart, see what's in it. This is so cheaply made, it's not even funny. The stickers are falling off of it. Oh, look at that. They got they got a shield on there. Yeah, that's a shield, all right. Right here, first thing that comes in is a fuse right to the diode bridge. No EMC filtering whatsoever. So this is the chopping device here. It's a little FET that does a bunch of chopping. This is the high frequency transformer. Then you got a rectifier, and you got a little chip on the other side here that determines whether there's a short, an open, or a legitimate battery to charge, and a relay which turns on if it sees some voltage. So zero EMC filtering inside this at all. Kind of grosses me out, actually. And again, these things in the wintertime, not just in the wintertime, but in the wintertime there's lots of these things plugged in, right? Because, oh, you got your classic car out in the garage. You don't want to take a chance on that battery going dead on you and having the battery freeze up. So you put one of these babies on. Cheap, right? $19.95. Perfect. Except for everybody within a block radius has an S9 on 80 meters. In the summertime, these things will charge things like lawn tractor batteries, electric bicycles, all sorts of stuff. Anyway, I probably won't be using one of these things for myself anytime soon. So that's it. I appreciate it if you guys stuck around with me till the end here. I'd also appreciate it if you could subscribe. We're well on our way to 1,500 subscribers and maybe to 2,000 within the next month or two. Maybe share this if you can, because I know this is a really big problem with these battery chargers. They're just cheap as, well, you know what, as cheap as can possibly be. And final comments here. So I guess that's all I really got to say. Well, one more thing. Don't buy one of these. Buy one of these. And this is a it's a great thing to have. It's really great to experiment with. Find out if noise sources are coming from someplace. There's quite a bit of attenuation in here. Plug it into your stereo. Plug it into your you know, whatever, your battery chargers, whatever. The only thing is you have to remember is when you make the choice of this filter inside, this one's only good for 3 amps. So this is not going to go in back of your 25 amp or 30 amp power supply that powers your ham rig. But it is a cheap and easy thing to build. The other thing I noticed is, which you might be interested in, is if you have a lot of old radios that don't have transformers in them or any kind of filtering, like say a transoceanic or some early Hallicrafters, this keeps a lot of garbage that's on the AC line from getting into the radio. I've noticed that. I've used this, and that's actually primarily why I built this. I'll probably make a bigger one. Anyway, thanks a lot for watching, and if you can, please subscribe. I really would appreciate it. Takes quite a bit of time to do some of these things, and you'll make my daughter-in-law and my son happy if you do. The next thing I think we'll do with the LISN is we'll look at some LED bulbs. We'll look at some. Let me see. Do I have them over here? I don't have them right here, but there's some interesting things to think about with LED bulbs. It's a question I get all the time. Wow, what bulb could I, you know, can you recommend a bulb? And I'm there, no, not really. Because in a lot of cases, it depends on how the bulb is installed. Pretty much the, wish I had them here. Yeah, they're in the other room. I'm not gonna go get them. Pretty much the little Phillips E27 screw-in bulbs. Those are pretty quiet. But there's noise, you know, right up close. You put your AM radio right up to anything and you're going to hear noise. But the question is, does it conduct well? You know, I mean, does it radiate well? No, it doesn't radiate. And they filtered the power supply so all that garbage can't get into onto the AC line. But again, look at this. This little thing is like a transmitter, and here's this crappy little dipole that it's connected to. And it can't transmit for beans, but wow, once you get it connected to the AC mains, where the conductive noise can now go to everything in your house and the power lines, and when you take this side here with its 18 inches of wire and connect it to a car body and the wiring in the car, huge, huge, huge noise. So please, one last thing, please subscribe if you can. I'd really appreciate it. And if you have ideas or questions or comments, put them in that comment section down there below. And let me know what you think about the t-shirt. Appreciate it. 73 for now. W1VLF. Signing off.